Welcome back, folks. We're looking at circuits that have BJT transistors in them. And hopefully we've gotten a little bit of an intuitive sense of what's going on with a transistor as far as moving from cutoff to active to saturation. But I want to start analyzing more complicated circuits. And I'm going to show you a circuit, and it's common enough to find in your textbook, and you can find all the formulas for the circuit if you want. But I want to write the equations for this ourselves as a step towards being able to write the equations for any circuit. So it's a little more complicated, and that's kind of how we learn. We increase the complexity. Okay. The other thing I'm going to do is not tell you what region it's in. So we'll have to figure that out for ourselves and analyze it correctly regardless. So here's a circuit. This is usually called a voltage divider bias circuit. It's a common-emitter amplifier if we were to stick some AC signals into it, but we're only focused on DC right now. Okay, so we don't know what region it's in. So we're going to assume the forward region, right? For starters. Okay. Assume forward. Okay, and if we assume forward, we can make our assumptions by replacing the BJT with the DC equivalent circuit. So I'm gonna copy this over like this, and we're gonna replace this BJT. It's above my head. Literally, not figuratively. Okay. With our DC equivalent circuit. Okay, so we're gonna have our diode there. I'm gonna reposition this. It's not moving, but just to make the drawing a little cleaner. Okay, we're gonna do that. We're gonna have our dependent supply with the current flowing down like that, connected to the collector, and then there's that resistor. I just moved it over a skosh, but it didn't change the way it was connected. Okay, what was that, 1K? 1K. Oh, I guess it's on the screen too. Okay, so we've got our DC equivalent here. Beta was 200, right? So this is 200 times IB, which is the current flowing into the base, which is going to exist right there. Okay, the current flowing into the base, just like that. Okay, now we analyze this one, and we can do this. It's a little more complex, but this is life. Okay, so let's see here. We've got, what nodes do we want to list off here? We've got a node here. Okay, this node, let's call this one B since it's the base. Okay, let's call this one E since it's the emitter. And then let's call this one C since it's the collector. Okay, and we have 4 nodes, so we need 4 equations. All right, we're also going to make the assumption here that if we're in the active region, this is going to be a forward biased PN junction, so that's 0.7 volts. And then let's get some currents here. That just look like this. Now, when I was taught this, and when I've seen others teach it, and I look at the textbooks, they go through a whole rigmarole about, well, we've got to Thevenize around the transistor and figure that out to reduce these two to a Thevenin equivalent circuit. And it works, but it's not consistent. And I really like consistency in my analysis. So I'd rather just apply nodal analysis rather than playing around with Thevenin equivalent circuits that have to be applied haphazardly. All right, so recalling that there's a voltage supply out here, right, connected to A. That's what that bubble gives me, right? That's a 15 volt supply. I want to always remember that that's what those bubbles imply. We start to write our equations. So I see a voltage supply, and I see a known voltage here. So I think I'm going to write 2 kVLs, and then I have to make up the difference with kCLs, so that I get a total of 4 equations because I have 4 unknown node voltages. So let's write some of those. Let's say VA minus 0 equals 15. Okay, that's one equation. And then the other one is VB minus VE equals 0.7. All right, those are my 2 kVLs. I'd say those were the easy ones to write, in my opinion. Okay. Now I have to write 2 kCLs, and I have to pick where they are carefully. A is connected to a voltage supply, so I'm not going to write that one. So is ground. I'm not going to write that one. B is connected to what I'm treating as a voltage supply because it's 0.7 volts. So I'm not going to write that one. And the same thing with E. So that leaves me with C. So let's write a kCL for C. And let's see here. That kCL for C is going to look like, well, this current's going in, so it's going to be VA minus VC over 2K. All right, and then I've got the dependent current. I'll scroll up a bit. I get the dependent current also leaving, and that's 200 IB. Okay, I have to write an expression for IB. That's equal to 0 because that's not one of my unknowns. So I have to be careful. I'm adding an unknown because of this, and that unknown is the control variable of the dependent supply. All right, so that current is here, and it's not through a resistor. It's through a diode. So I don't know the resistance. And that means I have to go find it another way. So if I want to find this current, it is part of the kCL for B, right? So now I might reconsider writing that kCL for B because I want to find that current. So I have this current going in, so it's VA minus VB over 20K. Okay, this current's leaving, so it's minus. Is this behind my head? Minus VB minus 0 over 80K. Okay, and IB is leaving, so it's minus IB. Now, if I had to do all this algebra by hand, I would solve for IB and I would plug it in here. But I'm going to let MATLAB do that for me. Okay, so this is just going to be an additional equation. I have 4 unknown node voltages, but I have a control variable, and this equation deals with that control variable. So I really have 5 unknowns, and one of them is the control variable now. Okay, so I'm going to use both of these equations in my system. We'll move over and we'll do this in MATLAB. If I'm feeling nice, I'll pause the video while I type these all out. Okay, so I need one more kCL, and I can't write it in any of the other places. This one added an unknown, but it was a necessary unknown to add. So I've got to look at this, and if I have a known voltage between 2 non-reference nodes, I get to treat it as a supernode. Okay, so I'm going to bound this region. That includes B and E, because that's what the diode is connected to. And we treat that the same way as a voltage supply. Okay, and I'm going to say that's my supernode. And I have 1, 2, 3, 4 currents flowing into my supernode. So I've got to write out those 4 currents for my supernode. Okay, super, and this is, the supernode is made up of B and E. All right, let's do that. let's say VA minus VB over 20K minus VB, and it is minus 0. I'll leave that 0 off this time. It's just minus 0 over 80K minus VE minus 0 over 1K, and then plus 200 IB. Okay, so I think I'm content with that. And that's going to be my fifth equation. Oh, it's equal to 0. Got to make it an equation. It's equal to 0. Okay. So with those 5 equations, 1, 2, 3, 4, 5, I can find the 5 unknowns. 4 of them are my node voltages, non-reference node voltages. 1 of them is my control variable for the BE junction, or for the dependent supply. All right, so let's see. Let's do that and this, and start off our script, okay? All right, set up our symbolic variables VA, VB, VC, VE, and IB. Okay, I'm going to write out the equations. I'll pause the video just to keep this a little more exciting, and see you on the flip side. Ta-da! Okay, so wrote a bunch of script. I started with my usual stuff up here. I defined the symbolic variables, and I included that control variable so that I could add that 5th equation in there. These should go through and check them out. Check them against the image that I gave you. These are the equations that I had written out when I started the analysis. All right. I solved them. I solved them, and I solved them for the 5 unknowns. Okay, and then just spit out those values. I even spit out the current for the base, because we had it. We should go use it. All right, so I run that, and I get a bunch of values out. Let's see, I get VA is 15. Yeah, no kidding. VB is 11.17. VC is negative 5.83. VE is 10.47. And then we have 52 microamps flowing through the base. Okay, so let's move this back over here, and let's get those on paper so that we can check our assumption. We assumed active. Maybe you're looking at it and you're like, hey, I already know the answer. But if you don't know the answer, let's go through the steps to figure it out for sure. Okay, so let's say check assumption. VA equals 15. VB equals 11.17 volts. VC is equal to negative 5.83 volts. VE is equal to 10.47 volts. Okay, those are my 4 node voltages, and those are the things I need to go find whether my assumption was correct. Okay, so let's say, well, what is VBE? Okay, and VBE is 11.17 minus 10.47, which is known as, well, it's 0.7, and it better be, because that was part of the system of equations, right? But I would call that one forward. Okay, and VCE, not VCE, VBC is the next one I want to look at, and that's 11.17 minus negative 5.83, and we would find that that is 17 volts. Okay, and that's positive. And we would say that one's forward. So if we're looking at that table, we would say, hey, given both of these, we would conclude that this is in saturation. And we would be correct. Okay, it is in fact in saturation. All right. The other thing we can do is look at VCE, right? VCE is equal to negative 5.83 minus 10.47. The emitter is no longer grounded. There's actually a voltage there. And that would give us negative 16.3 volts. Okay, and since that's less than 0, we'd say, hey, that's saturation. Okay, so the BJT is saturated. We got to figure out what to do. It means the VCE path is shorted. Okay, so all of this says the C to E path is shorted. Okay, so these values aren't right. Okay, that's not what's going on in the circuit. What is going on in the circuit, let's come up here. Let's grab the original circuit, is going to be different. And we got to go analyze it for that. Okay, so we take this and we have to redraw it. Okay, and one way we can redraw it is by saying the base and the emitter are still connected by a PN junction. Right? So we can draw that here and say, hey, this is effectively a diode, like that. Okay, and this path is now shorted, just like that. All right, so we got to reanalyze it. A, B, and this is now, oh, this is CNE because they're shorted together. So you gotta pick what you call it. I'm just gonna call it C. Okay, and we get some current directions going. And a current direction. That's a pretty sad looking diode, isn't it? Let's see if I can do better. Going for style points. Okay. And we assume that that's plus minus 0.7 volts. All right, so we still end up with a supernode in our analysis. It just looks like this. All right, that's our supernode. And we start writing equations. We only got 3 this time, so it's a little easier. VA equals 15 volts. VB minus VC equals 0.7 volts. And then we write the KCL for the supernode. Whew. Write the KCL for the supernode. This time it's made up of B and C. Okay, so from that we get 4 currents, 1, 2, 3, 4. VA minus VB over 20K minus VB over 80K. Sorry folks, my hand is cramping up with the stylus. Plus VA minus VC over 2K and minus VC over 1K, and that's equal to 0. Okay, so those are the 3 equations that I'm interested in, and from that I'm going to find voltages for VA, VB, and VC. Okay, so let's hop over to MATLAB, and I'm going to add a chunk to the script that, now making the correct assumption, we get the answer we want. Okay, the node voltages. So let's grab MATLAB and zoom out. And what I'm going to do is just, I'm going to use the same script. Okay, and I'm going to add a section down here. Okay, saturated. Okay, all of this was assume active. Okay, going to be much of the same stuff, so I'm just going to steal that. Okay. Don't go anywhere through the magic of time travel. Ta-da! Okay, nothing crazy here, just defining my symbolics. I don't need all of those. Those are the equations. I believe I have those entered correctly. Solve it, spit it out. Okay, so nothing new there. I'm betting you're getting pretty accustomed to that. Okay, so from this, we see that, yep, that agrees with what I got in the past. VA is 15, here's VB, and here's VC. So let's get those on the over here on the pad. Okay, and we've got 15 volts. No kidding, it's a 15 volt supply. It better be 5.95 volts and 5.25 volts. Okay, and that's actually what's going on with this circuit because it's in saturation. So I'd hang my hat on those numbers. If I really wanted to be confident, I'd go simulate it, I'd go build it, but I'm feeling pretty good about that. All right, so a little more complicated circuit. I walked you into it not knowing what region of operation it was in, because that's going to happen. So I want you to be able to figure out what region it's in, and I want you to be able to figure out what the actual node voltages are that are based on some kind of, well, we want to deal with reality, don't we? Not made up problems. Anyhow, all right, it's getting more complicated, but that's life, okay? We'll do a few more of these, hopefully to get you right with doing nodal analysis, okay, so that we can find the operating point of BJT circuits. Stay tuned and good luck, folks.